Oh, welcome back, everyone. We'll continue with the jailbreaking, and this time it's the Absinthe talk. Please welcome him.
Thank you, everyone, for coming to this second part of our talk. We're gonna just, we just introduce the second part. We had issues with the A5 because it's kind of different than in the first part, and we'll try to explain why it's different and how we managed to jailbreak it. So here is a summary of part one. We've seen that Corona A4 relies on the tethered jailbreak to inject the tethering payloads to the file system. That userland wrap code is started at boot time with a format string bug in the IPsec Raccoon service. And this is nice because we add this little feature from LaunchD to disable ASLR at boot time, which is right now with latest version of iOS not possible anymore. Also, one important thing about the HFS kernel exploit we talked earlier is that it has to be done as the root user, and it has to be done also out of the Raccoon sandbox. David will explain this afterwards. And this is required. And one little trick we used to just keep the sandbox at boot time is just to patch the Raccoon binary and just change 1 byte to modify the Raccoon profile to just to nothing. Yeah, in fact, to nothing. You just skipped the profile by just modifying the entitlements blob of the Mac O that weirdly were not checked by the kernel at that time. So now A5. As you know, certain of you, I mean, there's no tethered jailbreak on the A5. We don't have a boot level exploit for it, no limerain. We don't have this backdoor to inject our stuff to the file system. So as a result of this, also, we can decrypt the kernel because the AES keys are disabled when the iOS is booted. This makes things really harder for us to exploit the kernel and do the actual jailbreak, of course. Hopefully, we have found, with some luck, a way to use Raccoon again as an injection vector for the A5. But that implies that we need to get out of the Raccoon sandbox, because this time this is the original Raccoon we're trying to exploit, not the patched one, to remove the root file system, read-write, because by default, of course, it is just read-only. So, what is that? Okay, yeah, there's one slide missing, whatever. I'm introducing Joshua Hill, which will talk of how we managed to inject the payload.
Yeah, how we managed to actually get the exploits inside of the file system so Corona can run. The problem is we need a new injection vector so we can gain the initial code execution. The Corona files have to be copied onto the root file system so they can launch every time on boot through a launch daemon. The root file system is read-only, so we have to have some kind of code running in order to remount that first. More problems. ASLR, of course, is a big problem. We don't have any code running on the device. We have to find some kind of information leak. And of course, the sandbox profile. Well, we either need a way to inject commands into the current Raccoon configuration so we can include our payload, or and a way to bypass the ASLR to generate our route payload through some kind of information leak or some other way. The actual exploit here is in VPN settings. It doesn't properly validate the input sent through it. It never checks if you just stick a quotation mark and semicolon there. You can just add on new ones. So VPN settings are injected through config-d, which are passed into Raccoon. And the good thing about this is that the VPN settings can actually be written to the device using mobile backup too. They're stored in that preferences domain. Here's an example of the profile after it's been injected. See, just semicolon or parentheses, semicolon, percentage sign in, easy crash. Unfortunately, the user build we use is limited to 255 characters, so it's not really enough to stick our huge route payload in there. But we can use the include command and actually get it to load a configuration from another file. Only problem with that is sandbox profile, extremely strict. So there's very few places you can read or write to from within Raccoon. So we need to find basically some place that allows us to upload from off the device, but still allow Raccoon to read it based on sandbox. The payload. We actually found one directory. I thought it was in there. Also in the preferences directory, com.apple.ipsec, actually Raccoon can read from, and we can write to it mobile backup. So we're actually able to inject commands or inject the payloads that way, and then just inject the commands to load the file from there. I think it's guys.
Yeah, welcome back. So now, So now that we are able to set a configuration profile for the Raccoon daemon, which would trigger the exploit, we still have to execute it somehow. So this is where we needed to find a way that is actually quite of user-friendly in the manner of a jailbreak tool to be triggered. So what we did is did some research, and we found out that there's an on-demand feature for the VPN connection dialing that is actually designed only for certificate-based authentication. So if you would set a configuration profile and provision it to your device with a shared secret authentication, it would actually not accept the on-demand features. But since we just write the configuration using the mobile backup 2 protocol, we can just set these parts of the configuration to allow shared secret authentication and at the same time use the on-demand feature. So this is really cool because we now have actually a way to let the magic happen automatically. But since this automatically would mean we have to know an exact time when a specific URL or an IP address is requested. This is a little bit of unpredictable. So it's also the problem is that not every maybe system daemon is triggering a connection. So it's designed for the user. If he is in the enterprise network and opens the email client that will access the enterprise's email server, this would usually trigger a VPN connection. Same would be for Safari. If you just type in a URL that is defined as the trigger URL, this would also dial the connection. But since we try to make it really easy for the user, we actually thought typing in an address in Safari is just not epic, because it takes too long to type the address, and if it's misspelled, it's really not safe. So we thought of another nice feature which is called WebClip. It's basically a bookmark that resides on the springboard, and so you just tap this WebClip, which we provision together with the VPN connection using the mobile backup 2 protocol onto the device, and this WebClip will open a prepared web page that contains a reference to, we used an image tag that referenced our trigger URL. So it wasn't actually loading any image, but this is the defined triggering URL. So if you open this web page, this would just trigger Raccoon to start the connection. And since we prepared the configuration of Raccoon with the exploit payload, this would just execute the exploit chain. As Josh already mentioned, we still have to bypass the ASLR security feature of iOS. The problem is here that on every boot, the DOILD shared cache is slided every boot. So this means the address space of all the libraries that reside in this cache is basically shifted in a random way. So it's not really predictable. Secondly, the binary itself also has the same thing, but this happens on every launch of the program, which also makes it not really predictable. Then, since we are on an A5 device, which does not have the line run exploit, we cannot set the disable ASLR launch key, because at this stage we did not remount the root file system writable, so we have no access to change this specific entry for the launch daemon. Now, to bypass the ASLR, we just make use of a nice feature included in every iOS, which is called the crash reporting service. This is if a program crashes, producing a really detailed crash report with some useful information like a backtrace where the crash happened, and CPU registers, the base addresses of the libraries used, and so this is actually a gift, because we can now get some vital information for our exploit. What we do now is we need to somehow crash something, and this crash must happen and is at a specific place in the jailbreak process. Since we cannot rely on waiting for a program to crash, we actually have to force something to crash. And the easiest way to do this is actually to crash one of the services that is running on the device, or that can be started on the device, which are used by iTunes as well, like the AFC protocol or whatever service, backup, sync. There are really a lot of services. Now, during the implementation for the new mobile backup 2 protocol, which was initially shipped with iOS 4.0, I actually found a crash that is not really exploitable, but it is always happening because it's just a null pointer exception. There is the mobile backup 1, or just mobile backup service, which is still present on the recent devices. And actually, the problem was I mistyped the service name when trying to implement the mobile backup 2 protocol, and this crashed actually the old backup agent. And this is how we found a crash that was really suitable for our purpose. Okay, now that we are able to force a crash at command, basically, we still need to get this crash report somehow. And what we do is actually nothing else what iTunes also does. If a crash happens, the device stores this crash report. If you attach your device to your computer, iTunes will copy over the crash reports. And for this purpose, we have two services. One is the crash report mover, which will just move the stored crash reports from the original location to another location, which is then available as a ch-rooted environment for the crash report copy service, which is nothing more than just a plain AFC service that allows to access these files. You can copy them, you can delete them, you can even write new files into this location. Yeah, that's basically it. So now we can just copy all of these crash reports and you just parse them. And since this crash report contains the addresses for the libraries, we can pick one of the libraries and use a known address of a function to get the slide offset of the ASLR from the DYLD shared cache to being able to generate the payload needed for Raccoon. Yeah, this part is for David.
All right, thanks. So my part of the presentation is breaking out of the XMU sandbox. And as Josh and Nikias have showed you, that we now have the ability to, on a stock A5 device, to execute Raccoon with a configuration file of our choosing. Unfortunately, the stock copy of Raccoon is still sandbox. And in order to launch the kernel exploit, we'll need to break out of the sandbox. So this shows you how. So what is the sandbox? It's codenamed Seatbelt. It's based off the trusted BSD mandatory access framework, or at least part of it is. It's actually split into two different parts. One is a kernel extension called sandbox.kext, and the other is these mandatory access control. And the sandbox.kext is actually the brains of the sandbox, whereas the Mac framework is how the sandbox actually enforces the sandbox policies. So how does the Mac framework enforce sandbox policies? Well, in a lot of these kernel interfaces that face the user land, a lot of these calls, when the kernel is compiled with a config mac f flag, they all call these various different functions that check if that particular process is allowed to perform a certain action. So these Mac checks are enforced on a process-by-process basis. And as you can see, there's a lot of different checks and a lot of granularities in how much they can be, how access can be controlled. So as you saw in the previous slide, when you make any relevant kernel interface, call one of those checks before performing an action. And you can see in the previous slide that there are a lot of different categories. So basically it hooks into every conceivable part of the system. You know, the file, interaction with the file, POSIX semaphores, system5 message queues, sockets, like all of these things, IOKit. But the Mac framework doesn't really do anything by itself. what happens is that it relies on other parts of the kernel to register what are called MAC policies. And anytime any of the MAC framework callbacks are called, it just calls the callbacks into policies. The policies are basically a giant list of function pointers that the MAC framework is supposed to call into to determine if an action is allowed or not. So then we get to the sandbox kernel extension, and it is a registered MAC policy. When it's initialized, it registers itself as a MAC policy, and it has a giant list of functions that are called into it to determine whether a particular process is allowed to do anything. The way that the sandbox kernel extension determines whether a program is allowed to do something is in a few ways. First, processes can opt in through the sandbox API. There's a function called sandbox init that's part of the OS X library that can have a process opt in to a particular sandbox profile, which determines what things it's allowed to do or not. Entitlements, as you saw earlier, it's a property list attached to every single Mako binary on OS X and iOS that determines, that has a list of properties, entitlements that the process is allowed to do. And one of the entitlements is what sandbox profile to use. Or if an application is launched from bar mobile applications, which is where all the App Store apps are installed, then the container sandbox. The container sandbox is the default sandbox for App Store apps that's enforced. So profiles are managed by sandbox. These built-in profiles, they're managed by this additional daemon called sandboxd, which the kernel communicates with. But whenever a process requests to use a certain profile, the kernel asks sandboxd to tell it what exact profile, what exact settings to apply, what exact profile it is. And profiles are like compiled tiny scheme programs. They're extremely complex, and they can have very fine granular control over everything. And here's an example of the source code for a profile, and it happens to be the sandbox profile of the process that we're concerned with, which is Raccoon. And you can see that by default, it is not allowed to do anything. But it's allowed to access certain locations, such as library preferences. As Josh and Nikias have referenced, it's allowed to write to its own log files. And it's allowed to do certain other things, like access certain mock services using IPC and access certain shared memory areas here. So, so this is sort of a recap of what was stated earlier. Why do we care? As Raccoon, as the IPsec daemon, we're actually running as root. But because of the sandbox profile, even processes running as root are restricted in what they can do, as a security precaution against us, people like us trying to do stuff like this. So, but for the A4 untether, we didn't actually need to do anything that difficult to get past the sandbox, and the reason is because Apple made a pretty silly mistake. This is the entitlements for the Raccoon process. As you can see over here, it says seatbelt profile. Seatbelt is a code name for the sandbox, and it says Raccoon. So it tells the kernel, when you execute this Raccoon binary, apply the Raccoon profile. So that's great. But what we did was we just patched this 1 byte from profiles to prof3s, and this causes this key not to be recognized. And the sandbox profile is therefore not applied. How can we do this? How does this break code signing? It does not. Even if you just binary patch the entitlements for a process, it doesn't actually break code signing. Apple still recognizes Raccoon as a signed application by Apple, but it'll just execute it without the sandbox profile, which is weird. So are we done? All we need to do is just patch that 1 byte and we're out of sandbox, right? Well, not quite. The thing is that we actually need a way to get first the patched copy of Raccoon onto the iOS file system, and we also need to convince the iOS to execute Raccoon with a copy of our patch configuration file as root in order to do anything. And this is this is the way we did it in the untether. Is etc launchd-conf, which tells launchd, which is like process 1 in the iOS world, like init in the Linux world. And it tells it to launch, to load this plist, which tells it to run Raccoon, run this patch version copy of Raccoon with our exploit configuration file and disable ASLR. So that's great, and we could put those two files on the file system with limerain. But for A5, since they fixed the boot ROM exploit that limerain relies upon, we can't do that. But what we can do, as Nikias has explained, what we can do is we can convince the default version of Raccoon, using those VPN settings that he talked about, to run with an exploit configuration file that we can use mobile backup and other stuff to restore onto. So the only thing we need to do then is to get out of the sandbox while running as Raccoon so we can remount the root as read-write and to get the patch version of Raccoon onto the file system and then launch that patch version of Raccoon that doesn't have a sandbox. But in order to run the patch version of Raccoon that's not in the sandbox, we need to first escape the sandbox. So there's like a chicken and egg issue. So we need to find another way to escape the sandbox. Fortunately, the sandbox is not entirely without flaws. What we found is that the syscall ptrace, which might be familiar to Unix developers as a debugging call that GDB uses, for example, to debug other processes. Ptrace is not used that much on OS X because there are more powerful interfaces on OS X because part of the OS X kernel is mock. And what mock can do is actually have let processes talk to each other using VM underscore calls that let you basically, you could remap another process's memory into your own memory space. You can examine its threads. You can control the other process's threads and all sorts of powerful stuff that you can't really do with ptrace and that GDB on OS X uses. So ptrace on OS X is not very powerful, and actually on iOS it's kind of buggy. It doesn't really work properly. But since Apple doesn't pay much attention to it, since it's not very necessary, it's also quite unrestricted. So we have ptrace. What can we do with ptrace? Well, what we can do with ptrace is possibly use it to control an unsandboxed process. We're root, so we could possibly use ptrace to attach to another process that's not restricted by a sandbox and get it to do something for us. So this is just showing you that ptrace doesn't really have any sort of sandbox checks in it. The only check that it does for authorization is kauth authorized process, this call right here. And so this goes, the source of this function is right here. And for kauth process cantrace, which is what the previous function called, it just calls this function cantrace. And cantrace checks for permissions much like how Unix traditionally checks for permissions. You can't trace a process if it's the process that's doing the tracing, it's already being traced, or it's not owned by you, or is a set ID on exec, unless you're root. So those are very traditional Unix restrictions. There's no weird sandbox issues here. And since Raccoon is running as root, we basically have carte blanche to ptrace any process on the OS that we want. But unfortunately, as I discussed, ptrace on OS X is not powerful at all. It's not something that you would usually use for debugging. It can't do a lot of things that ptrace on, for example, Linux can. Linux can set breakpoints using ptrace. It can peek and poke memory. It can stop the process on syscalls. But the OS X version of ptrace can do none of these things. A lot of the functionality is broken. But what does work is pt continue. It can't single step through a process because on iOS, thread set single step always returns failure. Actually, it does nothing but return failure. So when it gets here, when the function gets here, it will always return error not supported, and then leave the execution. But before you do that, before it does that, it actually successfully calls thread set entry point. And all this function does is in the structure for the thread in the kernel, in the structure that saves the register state of the thread, it just sets the PC to whatever you want. So basically, what we can do with this is control the PC, control the program counter of any other process. So even it successfully sets the PC and then errors out, but the PC setting that it does set remains active. So what are the limitations of what we can do with this method? Well, we can control PC, but only on the first thread, because ptrace doesn't have any facilities for selecting what thread of a process we control. And the only register we can control is PC, because none of the other stuff with ptrace works. We can't set the registers on any of the other registers on that thread that we control. And also another thing that really bothered us and took us a long time to figure out is we can't switch between ARM and thumb mode. And this is IDA dump of thread exception returns, which is how all functions on iOS return from syscalls and so on. This demonstrates why you can't switch between ARM and thumb mode. Maybe people don't know about the ARM architecture, but there's actually two instruction sets, ARM and thumb. And ARM is a 32-bit instruction set, and thumb is a 16-bit instruction set. So if you try to, if you're in ARM mode and you try to jump into the middle of thumb code, then it's not going to work. And if you have if you're in thumb mode and try to jump into the middle of ARM code, it's not going to work either. You actually have to set a bit inside a special register called CPSR, the thumb bit, which sets the processor mode and the instruction set that it uses. And this function is how all of the processes return from syscall. So this part is load 0x40 into R4. And 0x40 is where the previous CPSR was stored. And this is stored into SPSR, which is the saved CPSR register. And when you return from an instruction, move LR to PC, this SPSR setting is restored to CPSR. So in that way, whatever thumb mode that was stored in 0x40 is going to be active after this function returns. So even if you can set PC, like a thread set entry point sets this value right here, and this gets written to PC. Even if you set PC, the thumb bit is still whatever it was when you entered when the process was interrupted, when there was a context switch. So this is why you can't switch between ARM and thumb mode using that method. So how can we use this control over PC for evil? How can we do what we want with it? So Raccoon is root. We can manipulate any other process, including non-sandbox ones. And we can control PC, so maybe we can use ROP. But for ROP to work, you need two ingredients. One, you need to control stack, and then one the other is you need to control PC. Yeah. So it's actually pretty interesting. We use ROP to set up a situation where we use ROP in another process. So we use ROP to launch another ROP. So here's how we selected our victim. Our victim process for Raccoon is notify-D. And notify-D is a core component of Apple's notification system. What it does is it allows a kind of a very generic form of IPC that has a very easy to use interface. You can use it to notify all processes in a system of some sort of system event, like the Wi-Fi settings changed or something like that. And almost all processes can talk to notify-D. And also they have access to notify-D's shared memory area. So if we can use this shared memory area to have Raccoon write right, an arbitrarily large stack for notifid's ROP into it, and then we can tell notifid to pivot to that shared memory area and ROP from there, so we don't have any space limitations. We can also get stuff onto notifid stack via mock IPC, which is how mock IPC is how every process normally talks to notifid. And also, another useful thing that we can do with notifid is that we can make it block deterministically and also have have whatever we want deterministically on the stack at the same time. So I'm going to show you, I'm going to prove these 4 points in the next slides. So this is the profile for Raccoon again. As you can see over here, we are allowed to look up the notification center mock service. And we're allowed to access the notification center shared memory area. So notifid is allowed to interact with, Raccoon is allowed to interact with notifid. And here is the source code for a part of notifid called service mock message. And it's the main server loop that listens to all the requests, all the mock requests coming in and responds to them. And as you can see, it receives a message over here and uses these stack buffers to receive the message. RBuff is where the received message sits, and SBuff is where notifid's reply is going to be. So our message comes in over here, and then it tries to send a reply over here. And an interesting part of the mock messaging system is that the queue for the messaging system by default is only 5 messages deep. So basically, if there's already 5 messages in a process's receive queue, and you try to send a 6th message, then the kernel is going to make you block until that other process decides to receive 1 or more of your messages. So all we have to do is send notifid 6 messages over here and refuse to actually receive any of its replies, and it'll just get stuck here forever. And after it's stuck here forever, we will know that whatever we sent is going to be in RBuff on the stack, and the reply, which will be based on whatever we sent, will be on SBuff in the stack. So in that case, we have all the ingredients for a ROP. We can control PC, and we can control what's on a stack very deterministically. So this is going to be an overview of our exploit. The way we wrote our exploit is actually with a very clever ROP generation program that Cyril wrote. It actually consists of several different macros that allows you to do common ROP expressions like call functions and load register from memory. It's almost like a ROP compiler targeted towards Raccoon format strings in particular. So it was very easy to generate all sorts of complex ROP programs in. I don't have time to take you through the full source of the exploit generation, the ROP generation, but basically the idea of the ROP inside Raccoon is that first we create a non-sandbox version of Raccoon and put it in a place where we can write in change mode so that it's executable. Then we have to find the notifid PID. Then we put notifid's main thread on the IPC thread. Because remember, we can only control the main thread of the victim process. And as it happens, service mock message is actually not the main thread, it's the second thread. The first thread is actually a thread that just does nothing but listens to POSIX signals like SIG user 1, SIG user 2, and does some, dumps some data when it receives those signals. So we don't want to control that thread. We want to control a second thread. So what we can do is we can make that thread end by changing its PC to underscore BSD thread terminate. I didn't put it on the slide, but this causes the first thread to terminate, leaving the second thread as the main thread, and then we can directly control that thread. So then we block notifid with our exploit IPC message, which has the beginnings of the stack, and then after notifid is blocked, we can write the rest of the ROP stack to the shared memory area, and then we can set PC to somewhere that does the proper thing to the stack that we set up using the exploit IPC message and the shared memory area, and launch the exploit that way. Actually, I'm missing yeah. Actually, no. I'll just talk about it later. So this part is where I basically walk you through the ROP that happens inside notifid that we set up. The painful search for ARM gadgets. The hardest part about this exploit, after figuring out how exactly we're going to do it, how we're going to use ptrace to control another process, is just searching for the gadgets themselves, because they all had to be ARM. They couldn't be in thumb, but most of iOS was written in thumb mode because it takes less space. But wait a minute, isn't notifid also written in thumb mode? Well, it is. But the problem is that whenever there's a context switch of a process, usually it's in the middle of a blocking syscall. And all syscalls, like it's doing mock message, it's waiting for a mock message or something like that. So it's in the middle of blocking syscalls. And all syscalls on iOS are actually executed in ARM mode. So basically, whenever you interrupt the process, it's definitely going to be in ARM mode. So we need an ARM gadget that can jump to a thumb location we pick, so we can start using thumb gadgets for the rest of the ROP. Or else we have very, very limited selection of gadgets that we can use. So this is the first one, gadget holy, because it took forever to find, like took days to find. What's so special about this one is that it actually pops the stack to exactly where the reply's message ID is, and it's a quite a long pop. And we can control the reply's message ID because in MIG, mock interface generator, which is a standard way of generating mock services using mock IPC. The message ID of a reply is always the message ID of the request plus 100. So if we send a request to notifid with whatever we want minus 100, then when notifid formulates its reply, then its message ID will be whatever we want. So we happen to find a gadget that sets PC to precisely where the reply's message ID is, thanks to Jay Freeman. You might know him as Sark. He actually didn't realize that he found the gadget. We double-checked twice because we've been looking for it forever, and it was like we had no sleep, but we finally found it. And this is I'm not sure if you can see this. Actually, I'm pretty sure you can't see this at all because it's in blue. But it adds A to the SP, then loads a bunch of stuff into floating point registers and double precision floating point registers, which take up a lot of space. And then it pops some more registers, and it pops a bunch of registers and PC at the end. And pop can do an ARM thumb switch. So whatever we put where we pop PC, we can switch into thumb mode from ARM or whatever we want. So this is actually the stack of notifid right when we interrupt it. At the top is mock message trap, which is the syscall. It's the wrapper around the syscall inside the libraries, the system libraries. And this is mock message, which calls mock message trap. And you saw that earlier in the earlier slide where service mock message called mock message. And service mock message is that function notifid that I showed you earlier. And this is what's on the stack. The reason, this is the address of the next gadget we're going to use, and it's positioned perfectly in the reply buffer's message ID. And the reason we did that is the minus 100 trick that I said earlier. And data 0 is make bad ID because this is not actually a valid mock message that notifid recognizes. So this is the state of the stack right before we set the PC of notifid using ptrace to gadget holy. And this is right after gadget holy, so it puts a bunch of stuff into these double precision floating point registers, and it pops PC into this next gadget. And this next gadget, the purpose of the next gadget is to jump across a significant portion of the stack to get from the reply buffer to the request buffer, which we directly control. The reply buffer is mostly filled with junk because Notify-D couldn't recognize the message that we sent. But the request buffer, we can actually fill it with mostly whatever we want. And so this is the gadget that we used. So this is the state of the stack right before that gadget is executed. So we popped all the other stuff off the stack earlier. Now we're right here. And now now that gadget has executed. And this sets up the next gadget, which, as you can probably guess from move SPR4, is a stack pivot gadget. We put the address of the shared memory in R4, and then this will pivot to it. And I described the gadget right here. Next gadget pivots the stack to the notification center shared memory and continues execution from there. So now we're actually pretty much free to do whatever we want. We have a ROP stack that's pretty much unlimited in size. Well, not unlimited, but 4 kilobytes, which is enough. And we can set up Notify-D to do whatever we want. And in this case, it is to do 2 syscalls really. The first is change ownership to change an ownership of this file, jb.plist to root, because launch control will refuse to load that plist unless it's root. And then afterwards, what we do is exec-l that plist. So this is pretty standard. We set up the LR for the change ownership call over here, and this sets up another LR. This actually calls the change ownership, and this returns to the previous part. And this actually calls the exec-l. So basically, we force launch control, which controls launch daemon, to load jb.plist. And the contents of jb.plist is very similar to what I showed you a few many slides ago, where the patch copy of Raccoon, which is not sandbox, is loaded, and also ASLR is disabled. So now we're running a copy of Raccoon that has ASLR disabled, that's not sandbox, and we're free to use ROP to force that copy of Raccoon to do whatever we want, which in this case is to do the sort of heap feng shui mount and unmounts that is required to exploit the kernel and then launch the rest of the jailbreak. So that's it.
Questions?
How did you get the shared memory address for your?
How did I get the shared memory address? Well, yeah, that part is we use some syscalls to get the first 44 memory regions of Notify-D, which we can do because we're root and that's not sandbox. So we write the structs. We write 44 of the descriptors for those 44 first memory regions into memory in Raccoon, and then we mend them to search for a area of memory that was read and write, write, and shared. And the first one that's read and write and shared is going to be the shared memory area of Notify-D.
Any more questions?
Can this be used for unfettered jailbreaks, for forensics?
Yeah, this is what we did for the untethered jailbreak. Nikias showed you how we could load the exploit configuration file onto a completely unjailbroken phone and actually you're talking about untethered jailbreaks. Yeah, so what we do is after this is done, we just load the etc launchd.com file and also we install the launchd plist. And this way, every time it boots, it runs that patch version of Raccoon with that exploit configuration that then patches the kernel. So every boot, it launches Raccoon, which then patches the kernel. So that's an untethered jailbreak right there.
Questions? Really? No more? Well, just give them a big applause. Oh, one more. No.
Hi. I don't have to. I don't want to ask any special question. I just wanted to say good work.
Thanks.
Right, thank him. And
Hey, what are you doing, guys? This is. Yeah, we're done. But just tell them that.
Well, we have one more thing to announce. We actually managed to finish the untethered jailbreak for the 5.11 iOS version, and we'd like to proudly announce as I said, we'd like to announce the untethered jailbreak for 5.11. The problem is, right now the green poison site is down for some reason, but we actually finished the work and it's available for download as soon as we manage to get the server back online. I think someone hacked us.
next presentation here will be Nicolas Gregoire in about 5 minutes.